Now let us move to the another topic, that is the field, the electric field of a polarized object. Here we will find out what is the net electric field produced by a polarized object. Before going to the discussion, we will come to know the concept of bound charge. Okay. Actually, a polarized object is, now we have seen a large number of microscopic dipoles aligned in a particular direction. The dipole moment per unit volume, that from the definition just now we have seen P(E)c is equal to small p divided by d2. Okay, actually this is a polarized object. Now the question is, what is the field produced by this object, or what is the total field produced because of this polarization, or what is the net field produced due to all these dipoles? Okay, that is a main heading of our discussion. Actually, the idea here is very simple. We need to find out the net electric field produced by this polarized object. For this, first what we will do is we find the field due to this individual dipole, then integrate to get the total. Okay. That is, it is much easier to work with the potential, because we know that electric field is a vector quantity. Therefore, if you calculate the electric field of the individual dipole, then integrate in, that will be quite difficult. Since the electric field is a vector quantity, we need to obey all the vector laws. Therefore, it is much easier to work with the potential. We will find the electric potential of individual dipole because it's a scalar quantity. So now our aim is first to find the potential due to this single dipole. Okay. Potential due to a single dipole in the earlier class and had secondary classes, you might have studied two charges, a dipole, that is minus and plus q charges. Dipole moment is along this negative to positive at a particular distance. Let's say r. At this point, the potential due to this dipole was given by P dot r cap divided by 4 pi epsilon 0 modulus r square. Or you can write this equation, you can modify the equation like r cap is equal to r divided by modulus r. If I substitute it here, this will be V is equal to P dot r divided by 4 pi epsilon 0. This will be modulus r cube. Okay. Here we need to know one thing, that is, here to find out this potential, I have chosen a coordinate system. That coordinate system, the origin of that coordinate system I placed on the dipole P, dipole moment P, at the center of the dipole moment P, because this is a single source. The source point means the dipole is a single, only one dipole is present here. But in the case of a polarized object, it consists of a large number of dipoles. So we cannot place the origin of the source point. Source point means here the source is the dipole. So the polarized object consists of a large number of dipoles. Large number of dipoles in the sense, if you take a small volume element, that it consists of a large number of dipoles. Here the dipoles are continuous distribution. Here the source point is not a single one, but here the source point is a single one. Only one single dipole is present here. Okay, that is, in such a case, in a polarized object, if we consider a single dipole, the potential due to that is a single dipole. We have to calculate in the following way. That is, if this is a coordinate system, and this is a dipole P. This dipole P is to distance R, and at a particular, here this is the point P where we are interested to find the potential due to this dipole. This is R prime. Okay, the coordinate of this dipole is R prime, and this is our R. This is nothing. R. This one is R minus R prime. Okay, this distance is R minus R prime. This is a point P where we are interested to find out the potential due to its dipole. This is a single dipole in a polarized object. In this polarized object, we are considering only one dipole of this polarized object. Okay. Actually, here by calculating the potential due to this dipole, this is the source point and this is a field point. Wherever the charge is present, the polarization takes place at that point, that place only. Okay. That is why this is a primed coordinate that is given for this dipole moment P. If we label potential due to a single dipole is dV, then here the potential due to this dipole of this polarized object can also be represented by dV. That is, this dV I can write in this way. Here the potential due to this dipole at a distance r was given by this expression. Similarly, potential due to this dipole at a distance r minus r prime can also be written in the similar fashion, that is r minus r prime divided by, here 1 by 4 pi epsilon 0 is there. Instead of here it was a r cube, or here that will be from the dipole to the point, here the distance is r minus r prime. R minus r prime modulus cube. Okay, now if I draw the picture of this body, the situation if I consider a small volume element, that is I mentioned this is a d tau prime, and if this is a r prime, and the point of interest that is here, this distance will be r minus r prime, because this is a distance r, this is distance r cap, r prime, r minus r prime, this is r. Okay. If I consider a small volume element d tau prime and it consists of a dipole p, then by the definition we can write the polarization. By definition, polarization can be written as P is equal to dipole moment per unit volume, that is, this P can be written as, okay, this P here, I would like to mention one more thing here. This P is the polarization that takes place in this volume element, that is, its coordinate is r prime. Therefore, I need to mention this is a r prime. Okay, I will write here r prime is equal to dipole moment small p. The unit volume is nothing but d tau prime. Okay. If I give the equation, this is equation number 1 and this is equation number 2. Next, I will replace this p by this quantity. That is, here I will do this small rearrangement. This small p can be written as p r prime d tau prime. If I give this is equation number 2, I delete this equation 2. Next, I will put this equation 2 in the equation. That means I will replace this p by this this equation. Okay. For the convenience, I rewrite those two equations here. Okay. Now put equation 2 in 1. Therefore, our dV can be written as 1 by 4 pi epsilon 0 till p r prime dot r minus r prime divided by r minus r prime whole cube d tau prime. Just I have substituted here. This dV is a potential due to the dipole moment, potential due to the dipole contained in this volume d tau prime. Now I need to find out the potential due to these whole dipoles, or the potential due to the whole polarized object. Therefore, so potential due to the whole polarized object, I can write this just nothing, it's you do the integration over the volume V dV, that is 1 by 4 pi epsilon 0 V P r dot prime r minus r prime cube d tau prime. They say this is equation number 3. Here I will introduce an interesting result, that is this quantity, that is quantity r minus r prime divided by r minus r prime whole cube. this can be proved to this result, is r minus r prime. Okay, I will derive this relation for you. It will take a few minutes. However, this is quite it will be useful for you. So now we have to prove r minus r dash divided by r minus r prime cube is equal to del prime 1 by r minus r prime modulus. This is our RHS. RHS, we can start from the RHS. Then we can arrive at this result. Okay, here the del prime operator can be written as dou by dou x prime I cap plus dou by dou y prime j cap plus dou by dou z prime k cap, and r can be written as x I cap plus y j cap plus z k cap. R prime can be written as x prime I cap plus y prime j cap plus z prime k cap. Okay, now we need to find out r minus r cap. That is r minus r cap can be written as, just to subtract x minus x prime I cap plus y minus y prime j cap plus z minus z prime k cap. If I take the dot product of r minus r prime, that is dot r minus r prime, that is x minus x prime I cap plus y minus y prime j cap plus z minus z prime k cap. Once again, x minus x prime I cap plus y minus y prime j cap plus z minus z prime k cap. Then this quantity, this is like r dot r is nothing but r square. The similar way, this I can write as r minus r prime square, or I can write modulus of r minus r prime whole square, x minus x prime I dot x minus x prime I dot, that is x minus x prime whole square plus y minus y prime whole square plus j dot j is equal to 1. Then z minus z prime dot z minus z prime, okay, that is z minus z prime whole square. The required quantity is r minus r prime modulus. R minus r prime modulus is the square root of this quantity, that is x minus x prime whole square plus y minus y prime whole square plus z minus z prime whole square. Okay, now we have the this quantity now we have, and we obtained these two relations. Just start the operation. I have copied the relation here, that del prime is this dou by dou x prime I cap dou by dou y j cap dou by dou z prime k cap, and 1 by r modulus of r minus r prime, this 1 by root of x minus x prime whole square, y minus y prime whole square, z minus z prime whole square. In the next step, repeated the same dou by dou x prime, that is del prime operator. Then the square root I have written as power minus 1 by 2 for the ease of the differentiation. Okay, now the first term, dou by dou x prime differentiate with respect to differentiate the x minus x prime with respect to x prime. Therefore, this is a dou by dou x of root x means, or x power 1 by x power n means n x raised to n minus 1. You can use that relation. That is minus 1 by 2 into n x raised to n, that is n x by 2 into x minus x prime whole square plus y minus y prime square plus z minus z prime square n x raised to n minus 1, that is minus 3 by 2. Here we have used this relation. This is d by dx of x raised to n is equal to n x power n minus 1. Now we have to differentiate this quantity with respect to x prime. That is 2 into x minus x prime into differentiation of minus x prime, because with respect to x prime that is minus 1, and with the I cap. Okay, plus now we have to differentiate the second term. Once again, this is nx raised to n minus 1, therefore this will be minus 1 by 2 into x minus x prime whole square plus y minus y prime whole square plus z minus z prime whole square whole power minus 3 by 2 into 2 times y minus y prime, and differentiation of with respect to y prime, that is minus 1 then j cap. Once again the differentiation for the z minus z prime whole square, that is the first unit will be same, x minus x prime whole square plus y minus y prime plus z minus z prime whole square minus 3 by 2 into 2 into z minus z prime into minus 1 k prime. Okay, now here these two will cancel, this minus will cancel, this minus will cancel, and this 2 and this 2 will cancel. Here also this minus cancel, 2 and 2 will cancel. Now if you write this equation, this will be x minus x power, this quantity is common, x minus x prime whole square plus y minus y whole square z minus z prime whole square minus 3 by 2. This is common in all the terms, therefore we can take it outside. That is x minus x prime whole square plus y minus y prime whole square plus z minus z prime whole square power minus 3 by 2. We can take it outside. Then remaining term is x minus x prime I cap plus y minus y prime j cap plus z minus z prime k cap. Okay, all the terms are positive. Now this relation you can write like this is 1 by x power 1 by 2 into x, that is 1 by 2 power x1. This will be 1 power x power 3 by 2. This x power 3 by 2 is nothing but this x power 3 by 2 is nothing but x power minus 3 by 2. Similar fashion we can write this is as a this x power 1 by 2 can be written as root x into x power 1 is x. Similar fashion I am going to write this relation, that is root x means I will write this as 1 by root of x minus x prime whole square plus y minus y prime whole square plus z minus z prime whole square. Then one more quantity will be here, that is x. X means x minus x prime. Because this is power 3 by 2, which is root of 1 by 2. Next x minus x prime. This is square root quantity can also be written like root of this quantity can be written as x minus x prime. This quantity can be written as r minus r prime modulus. This is nothing but r minus r prime modulus. Okay, this is r minus r prime modulus, and this quantity, that is, this is nothing but the square of this quantity, or we have x minus s prime, like we have this quantity r minus r prime mod square, r minus r prime mod square. So the del prime 1 by r minus r prime can be written as r minus r prime divided by modulus of r minus r prime, the square, and 1 income cube. So actually, let us from where we have come, let us go back. Actually, we have come from this point, that is question number 3, where we were looking for the substitution, and I have already mentioned, I will now we got the proof. We can replace this quantity r minus r prime by this expression. Now it is the proof is, I hope the proof is clear for you. Now let us give this is equation number 4. Let us put equation number 4 into 3. Put equation number 4 into 3. If you substitute, this will be v equal to 1 by 4 pi epsilon 0 v p r prime dot, instead of this quantity we will substitute del prime 1 by r minus r prime 1 d top prime.